Hello, my name is Frances Alfonso, and I'm going to be presenting the work titled Periodic, Quasi-Periodic, and Blow-up Regimes in a Nonlinear Mathieu Equation with Distributed Delay. This research I have conducted under the guidance of my advisor, Dr. Choudhury. We are both coming from the Department of Mathematics at the University of Central Florida. Now, to introduce, let's first present the equation we're going to be investigating, which is a nonlinear differential delayed equation. This equation right here, where A, B, C, delta, and chi are parameters. Now, why investigating this equation? In general, we shall find that using averaging is mostly successful in identifying parameter regimes with very different types of dynamics. Those parameter regimes will be hard to identify otherwise in any system that has multiple parameters like ours. There have been several special cases of this equation that have been studied in the past, like the study by Bad and Su in 1966 and that by Insperger and Stepan in 2002. We introduce here and study the equation with an integral delay, which is of course a time-varying delay that's done by Hamdi and Behak in 2018. But also the method of averaging has been useful to generate stability charts in the past for other versions of this equation, as was presented by Morrison and Rand in 2007. Now, going back to the equation, if we define z of t to be this integral and then y of t to be x dot, we can represent the equation as the system that we have right here, where x dot equals y of t, and then of course y dot is the one that has most of the information from the original equation, with the difference that now we have z, which is the integral part due to that transformation. Of course, z of t is going to be equal to chi times x minus z. Now, let's go ahead and do the averaging process. We shall introduce a small parameter epsilon, and we are going to the tune of the 2-1 resonance by setting delta equal to 1/4 my epsilon delta 1. Therefore, the system now reads x dot equals y, then y dot equals, we have pretty much the same expression, only that now we have, instead of b, beta, instead of delta, we have the delta 1, and instead of alpha, sorry, instead of a, we have alpha, and instead of c, we have gamma. Because we have said that a equals epsilon times alpha, and so forth. When epsilon equals 0, the original equation reduces to the x double dot equals minus 1/4 x of t, which then has the solution x equals the amplitude a times cosine of t over 2 plus the phase phi. Because of that, the entire system has this solution. And of course, for epsilon greater than 0, we look for a solution in the same form. But now treating a, which is the amplitude and the phase, as time dependent, and therefore we're going to use variation of parameters. Variation of parameters in the same way as in the monography by Verholz in 2005. And all steps are in depth in there, and that's how we get a dot and phi dot, which are these expressions with a new function capital F, which is nothing but the term that was multiplied by epsilon in the previous equations. And of course, x, y, and z are the ones given by the solution of the system for epsilon equals 0. Now, for small values of epsilon, you can use averaging, which is basically substitute the right-hand side of the previous equation by their average over the 2 pi period of the forcing function. That's why we can say that a dot and phi dot are going to be approximately these expressions here, which are, again, nothing but an average of what we had. Now, once we integrate there, we get these way nicer expressions where I would like to emphasize the fact that we have an epsilon that's multiplying both of them. And we have this term here, which is 2 chi divided by 1 plus 4 chi squared. And then down here, we have the same thing multiplied by 2. Because of that, we can then rewrite and say that a prime equals a times alpha over 2 times sine 2 phi minus beta chi prime, and another expression for phi prime. Now notice that those primes here, sorry, I meant chi hat. Those primes here represent differentiation with respect to the slow time, which is eta equals epsilon t, and then chi hat is that expression that repeated itself on both the previous equations. Now, we can also transform this system, which is in the polar coordinates a and phi, into rectangular coordinates. Let's name them u and v, and so we can get an alternate form of the slow flow equations. This alternate form is invariant under the transformation uv comma minus u minus v. So any fixed point in here will actually mean that we have two fixed points, the uv and the minus u minus v. Now let's analyze the slow flow equilibria for their stability and bifurcations. To find slow flow equilibrium points, of course, we set a prime and phi prime equal to 0, and that leads to the condition on a squared, which is r. Now, this condition, as you can see, is quadratic on r. We have this term that's multiplied by r, this term, which is the one that's multiplied by r, and this one multiplied by r squared. Because it is quadratic on r, we can solve, and of course, we'll have two solutions using quadratic formula. Those two solutions are given by this expression with a plus or minus, differentiating the two solutions. And of course, if we want to have a real r, we must require the radical inside this square root to be positive. Because of that, we have the condition that the absolute value of chi hat should be less than or equal 1/2 the absolute value of alpha over beta. For us to have non-trivial equilibrium points, r must be non-negative. Actually, r should be positive. So we must have this relation right here with delta 1. If we wanted it to be positive, we of course will have just the less than strict. So this will give us two conditions. The first condition, the positive one, will guarantee the existence of at least two non-trivial equilibrium points, a pair related to a positive u and v right here, and then at least two more if this condition that satisfies the one with a negative. Now, to analyze the local stability information, is useful to use the Jacobian matrix and its trace and determinant. Now, the Jacobian matrix for this system is given by this matrix right here. And just thinking about the trace right now, notice that if you add the position 1, 1, the position 2, 2, the first term of both of them is the same one with a different sign. That's why we get that the trace of the Jacobian matrix is -2 beta chi hat, while the determinant being evaluated at one of the non-trivial fixed points, or both actually, is given by this expression. You can see the plus or minus here coming from both the plus and the minus of the non-trivial fixed points of the condition on R. Now, because this trace does not depend on R, it will be equal to 0 for all slow flow equilibrium points whenever beta equals 0 or chi hat equals 0. Besides, the determinant of J is going to be equal to 0 when this condition, this equality here, is being satisfied, both with the plus and the minus. But this equality, as you know, let's look at it, it just means that R equals 0. So the change of stability associated with the determinant of J equals 0 will occur only at the origin. Therefore, we expect that those surfaces where we are marking the presence of real solutions for the equation on R, those will be saddle node bifurcations. A change of stability and a possible half bifurcations will occur when beta equals 0, which is the condition for the trace to be equal to 0 if the determinant is greater than 0. And the surfaces related to delta 1 with the positive and the negative sign are conditions for pitchfork bifurcations. So let's go ahead and check on a numerical example how these things show up. So in the following calculations, we're going to consider that alpha and gamma are equal to 1, epsilon is a small number, 0.05, and then there are several combinations of the other parameters. Mostly what we did was to pick one point and then another point on the negative side of the beta. You will see that chi is the same, and then delta 1 is pretty much the same. For all of those, it's just that we're changing the beta there. Why are we doing that? Because for alpha and gamma equal to 1, these are the surfaces that we obtain. These two planes are the planes for the trace to be equal to 0. So chi equals 0 and beta equals 0. You can see them here. And then the orange surface is the one related to delta 1 with a positive sign. And then the blue surface is the one related to delta 1 with a negative sign. That means that the origin should be a fixed point for all 6 points of the parameters space here, but then there should exist at least another fixed point, another couple of fixed points for these two, and another couple of fixed points for these 2 points down here. Now, this is what we're expecting. We expect that if the slow flow goes to a stable non-trivial fixed point, then the solution of original system should be a periodic function or a periodic solution. If the slow flow goes to 0, then that means amplitude depth and the averaging ansatz should also go to 0. And if the slow flow goes to a periodic solution, then it will mean that the averaging ansatz is two period quasi-periodic. So in the next figures that you will see, first thing we show is u in time, v in time, then u against v, and finally x in time, x being the solution to the original equation. So in the first state, we're taking a point that is close to the origin and we're checking what happens to the slow flow and what happens to the original function. As you can see, the slow flow goes to 0. You can see the behavior of both of them going to 0 here. That means that that's amplitude depth, and therefore the solution to the original equation goes to 0 or vanishes. The moment we cross the boundary of beta equals 0, so now we get the same values, but for beta equals 1, you can see that the solution of the slow flow explodes, and the same thing happens to the solution of the original system. Now let's check what happens inside the orange and blue surfaces, which are the ones that relate to the pitchfork bifurcation. So what happens is that you start with a point that is close to 0, but instead of going to the origin, it goes to another fixed point that we know exists. Notice the behavior here, it goes to 0, but then from 0 it goes out and it approaches a different fixed point, the one that we know will appear there. And as expected, the solution to the original system is a periodic solution once you let the time go on. What happens once you cross the barrier of the beta equals 0 plane? Well, the solutions of both the slow flow and the original system explode again. What will happen if we start near the origin? Once we go below the delta 1 equal surface that we saw, the blue surface with a negative sign, well, both the u and v go to 0. You can see the behavior right here, and because you are approaching the origin, then that means amplitude depth and the solution of the original system also goes to 0. What happens once you cross the beta equal 0 plane? Well, both the slow flow solution and the solution to the original system explode again. Now let's check what happens to those non-trivial fixed points where they can exist. So for instance, the one related to the positive sign, those that can exist below the blue surface, actually was the orange surface. Well, you start near one of them, near one of those fixed points, and you can see that the solution of the slow flow goes to a non-trivial fixed point. And as expected, the solution of the original system reproduces that and goes to a periodic solution. What happens once you cross the barrier of the beta equals 0 plane? Well, again, solution of the slow flow and the original system explode. Once you go still for this kind of fixed point below the blue surface, well, same thing. U and V are approaching a different value, or value that is not 0, I mean. Therefore, you can see the behavior of the UV solution here is approaching a fixed point, but it's non-trivial. Therefore, the solution of the original system goes to a periodic function. Once you cross the barrier of the beta equals 0, so beta equals -1, again, both the solutions of the slow flow and the original system explode. Now, what happens to that other pair of non-trivial fixed points? Let's get that we are starting with one point that is near one of those. As you can see, U and B, this time we're considering V negative. U and B are in here. You can see that the solution of the slow flow is getting to that point. However, the solution of the original system goes to 0. That is because for that specific parameter set, the origin is also a sink, so it attracts solutions. Now, what happens once we cross the barrier of the beta equals 0 plane? Well, we get, again, that the solutions for the slow flow and the original system explode. What would happen if we were to consider values of the parameter that lead to larger amplitudes? For instance, let's get alpha, beta, chi to be large, gamma to be the same, and then epsilon to be small as well, 0.05. Well, what happens is that we get a slightly larger amplitude for V, as you can see here. That larger amplitude then provokes that the fixed point is way above compared to the other ones that we have. And that generates then that the solution to the original equation is not a periodic function, although this is what you would expect from a non-trivial fixed point. Why is that? Well, that's because this is a large amplitude here. So as final comments, we're able to use the averaging to identify parameter regimes with way different types of dynamics for our integral delayed equation. This is otherwise something difficult to do for systems where you have multiple parameters like this one. The numerical results show that the behavior of the solution of the slow flow together with the averaging ansatz mostly correctly predict the dynamics of the original system. However, where do we find exceptions? Where there is large amplitude for the non-trivial fixed points of the slow flow or large amplitude for the predicted solutions of the slow flow. This averaging ansatz essentially fails in these cases because the system variables no longer evolve slowly. That's the main thing. And hence the evolution equations cannot correctly be averaged. So thank you for listening to this talk, and we're definitely going to be available for you to make questions if you have any. Here is a list of our references. Thank you.